Welcome everyone to the webinar today. Today we're going to have Dr. Robert Hilton present Measuring Breathing Rocks, Carbon Dioxide Release During Sedimentary Rock Weathering. And a little bit about Dr. Hilton. He's a geochemist and professor of sedimentary geology at the University of Oxford in the UK and lead of the Rock CO2 project. I think that's all I'm going to say about that. Actually, I had quite a lengthy bio for him, but I think we're going to just jump right in. And for people who got multiple emails with their webinar information, I apologize. I had tried a new approach and it didn't work well, but at least you all know. So welcome, Dr. Hilton. I've been looking forward to this for a long time. We all have here. So I'll let you take the floor.
Great.
Oh, I'm sorry, I do have to interrupt you. For anyone who has questions, please put them in the chat. We are going to let Dr. Hilton present all of his research and his data, and then you can either ask questions live at the end, or you can put them in the chat and we'll address them at the end of the presentation. And if there's any we don't get to, we'll be sure to have him answer them, and we will respond to you via email. I apologize. Go ahead.
Great. Thank you, Carrie. Thank you for organizing this, and I think also thank you generally for putting together this this program, because it's really interesting as a way to bring researchers together who are interested in CO2 transfers and using the kind of equipment that that we all kind of share, but we're using them in different ways. And I thought that was a really, exciting way to reach a wider range of interested people. So yeah, not knowing backgrounds of anybody here, I'm going to try and keep it so that you can follow, but also I'm not going to dumb it down. So I'm hoping I'm going to be able to combine those two things, and you're going to be able to hear about something interesting, which in our field here we're kind of thinking is right at the edge of what we're trying to understand and really try and push forward. And so I have this title, Carbon Dioxide Release During Sedimentary Rock Weathering. And this is what we've been focusing on in this Rock CO2 project, which is funded by the European Research Council. And then the image behind is actually showing a landscape of these rocks exposed. And this is where we think these reactions are happening, and we have CO2 being released from this type of rock. And I've said breathing rocks, which I guess might seem a bit of a strange way to put it. We're talking about rocks as inanimate. You might picture that they're just an object. But actually, the processes going on are kind of analogous to respiration, which is what we're doing all right now, breathing in air, taking the oxygen, combining it with organic material inside of us, releasing CO2. But actually, that's what's happening in these rocks as well. We're using oxygen to react these rocks and end up releasing CO2. Anyway, more of that in a moment. But before I go on, I just want to thank the funders I mentioned, the RC, NERC. I also started this research project at Durham University in the UK before moving to Oxford last year. And also just to really flag two key collaborators on this research, Guillaume Soulet and Tobys Roylands. So Guillaume Soulet was a postdoc on the Rock CO2 project, and Tobys Roylands has just recently submitted his PhD, and he was a PhD student on the project as well. And also our collaborators in France, Bastien Plotz and Caroline Laboutier. Plus, I'm going to talk a lot about Mark Garnett, who's at the NERC radiocarbon facility, who has developed a lot of the techniques that we combine to enable us to get to this. And he's obviously also driving some of the science questions as well. It's been a great team to work with. And then just to flag, the Rock CO2 team it's been really enjoyable working with this range of people. And so I won't talk about a lot of the work that's going on and is we've managed to complete, but just the flag that the bottom left there, you see Tobys, and next to him in the hat is Guillaume. So I'll be presenting work that they've been leading as part of the Rock CO2 team and project. Yeah, so let's put it in a bit of context. Where does this research sit and why are we doing it? Well, so this is the general framework that we're thinking about. We're talking about how two processes, erosion and weathering, which move material around and alter it at Earth's surface, actually move carbon around as well. and these contribute to what we call the geological or long-term carbon cycle. So on this kind of schematic, the first thing I want you to spot is that we've got this arrow coming out of a volcano, and this is corresponding to a carbon dioxide release of CO2 from the Earth into the atmosphere. And over time, if this just kept happening with nothing else to kind of counteract it, we'd end up with very, very high CO2 concentrations in the atmosphere over these geological timescales. We're talking about millions of years here. But actually what happens is there are a suite of reactions where rocks are chemically altered, and it moves CO2 out of the atmosphere and puts it into water, into a different molecule. And then we transfer that molecule to the oceans, where we can then make new sedimentary rocks, and we draw down that carbon. So I think I've got a little cartoon to show in a very noddy way, but here's our CO2 coming out of the volcano. It's in the atmosphere, and actually then it is used in a reaction with rocks, and it gets converted into a different compound, which is transported into the oceans, and then actually eventually transported into a new kind of phase in rocks. So this has been a kind of textbook view how we teach the geological carbon cycle. But what we've been doing amongst us, there's a number of groups around the world looking at this in earth sciences. We've been thinking about other processes that are important besides those that I've just described. One I'm not going to talk about today is another way to move carbon out of the system on these long time scales by burying organic material in sediment. So the remains of plants in the ocean, plants on land can be buried for millions of years, and this also draws down CO2. What we're interested here is though when these rocks are exposed at the surface, they also result in two ways in which CO2 can actually be released from rocks. So whereas I just described earlier that the rocks were helping to draw down CO2, there are actually these two other reactions that kind of counteract that. And the way that we've been coming at this is that we don't really understand those processes particularly well. We don't know how large the fluxes are, the natural fluxes are, and we don't know what might control them. So why might those CO2 fluxes change over time? So hopefully you might have already be familiar with these things, or if you haven't, hopefully that was interesting. And then the why, well, CO2 concentration in the atmosphere, as shown on this graph, is a major control on Earth's energy budget. It controls the surface temperature of the Earth through the greenhouse effect, and is a massive control on global climate. Here I'm showing a graph of how we've reconstructed CO2 in the geological past. So maybe I'll just check. Carrie, can you see a laser pointer? Yep. So in this period here, yeah, great. We're looking at ice core records where we've got CO2 in ice cores trapped in ice, and we know how much it's varied. Here we've got other geological ways. So this is going from 1 million years ago to 50 million years ago. And then this is looking even further back in time. Now, don't focus on the uncertainty and the scatter here. That's because we're reconstructing something. What I want to point out is that CO2 has varied over these time scales. And it's really important to understand how the carbon cycle has driven that change and how it also responds to that change. And one of the reasons for doing so is to understand this natural variability so that we can better see how our own actions are impacting the carbon cycle. So by burning fossil fuels, we're providing a shortcut in the carbon cycle, a bad one, that releases CO2 rapidly, far rapidly than we've seen in the geological past. And this is causing us on the right-hand side to increase CO2 concentrations in the atmosphere. So the geological carbon cycle and knowledge of natural processes can help to inform us about where we're heading, if you like. So that's one reason we do this type of research. So yeah, just come back to that figure. It's these purple boxes we want to talk about. There's lots of jargon here, and I'm going to unpack it. It's going to probably remain complicated, but hopefully I'll unpack it and you can follow what we're doing and why. First thing to say is weathering. I've used this word a couple of times already. What is it? Where does it happen? And actually, most of us are familiar with weathering because one of the products of weathering is soil. So anytime you're out and about and soil gets stuck to your boots as you're hiking around, soil is one part of what it makes up soil are chemically and physically altered rocks that were once rocks and they've been made smaller and they've been chemically changed. And those reactions, so this kind of shows it with this diagram, right? We've got this column, we've got rock at the bottom, and actually the rock is being changed through interaction with water and air and life as well. We've got roots, we've got microorganisms that we can't see, and they're all helping to react these rocks. So when I talk about weathering, that's what I'm getting at. The other consequence of weathering is it can transfer phases and elements from, say, the atmosphere into rivers, or the other way around. It can actually transfer phases from the rocks into the atmosphere. And so this is a zone where we're really interested in these interactions between the geological carbon cycle and the atmosphere at that time. So in this talk, I'm going to have kind of three main themes for about half an hour. I'm planning, hopefully, for the next half an hour or so. So I'm going to talk about this release of CO2 as we weather these rocks. But a key thing that we've been struggling with is how do we actually measure this, and how do we actually get the measurements we need to understand the process? And that's what most of this talk is going to be about, a bit of a backstory about how we were thinking about this and some of the technical challenges we had to do this. There's a bit of what we call geochemistry in here. We measure isotopes of carbon. You might have heard of radiocarbon. That's one carbon isotope that we can measure, and it's very helpful for us in this application. I'm going to talk about a field area in France where we focused a lot of work. Actually, I'm going to tell you what the main scientific finding straight away. We find that temperature, changes in temperature correspond to changes in CO2 release from these sedimentary rocks. And before we did this work, that wasn't recognized at all. And so this is a really important outcome of what we were able to do methodologically. And then just provide an overview and obviously take questions. So let's just look a little bit more. There's going to be some chemical equations here, but I think it's important you can follow the carbon through them and we can see what's going on. So what I'm talking about, two processes when CO2 is released by weathering rocks. What the first one is, if we've got bits of plants or animals, they've been buried in sediments and they might be found in rocks now, and they're millions of years old. But those bits of organic carbon can be oxidized. So this thing here is a simplified formula describing organic carbon. Oh, apologies, I'm just getting a phone call. Apologies for that. And if we oxidize it here with oxygen, we can release CO2. And this is so-called georespiration. It's an equivalent of what we're all doing right now. The other cascade of reactions is a little bit more complicated because it involves two reactions being linked. The first is if we take a mineral, a sulfide mineral, which we find in rocks. This is often termed pyrite or fool's gold. And this mineral, when it reacts, can produce an acid. And the acid can then attack a carbonate grain, a carbonate mineral, which also contains carbon in the rock, and this can release CO2. So there's another way that we get the CO2 being released. So here, again, don't worry too much about this, but I just wanted to show for completeness. Here's our iron sulfide mineral that we react with oxygen and water, and we make a new mineral here, but we also make this thing, and this is sulfuric acid. And this sulfuric acid can be used to dissolve this mineral here, which contains carbon. And this carbon, again, has been stored for millions of years and now is being released as CO2 into the atmosphere or water column, whatever else. We also get some other things out of this reaction. But yeah, these are the two main sources that we might expect to find. So how can we actually start to measure some of these things? And this is what had been, I guess, motivation for our project was to better understand these. We need measurements from the landscape where these things are happening. So this is a visual image where an image where you can see visually the reactions that are happening. So the dark bits of this image towards the left, like the blacky kind of bluey color, are rocks that contain lots of organic carbon. And that organic carbon is quite fresh and it hasn't really changed for millions of years, been stored in these rocks. The orange bits, these rocks have been weathered chemically and physically, and some of the carbon in those rocks has been released. And so we've had this process of weathering, releasing CO2. So I'll just again remind you an equation that might look like this. So how can we measure this process, try and understand it? Well, we kind of have three options. The first is we can look at what's there, and that's the thing that's been left behind in the environment. And so here in orange, orangey color, we have this weathered material. Now that's really informative. We can understand what's left behind. We can see whether it tells us about what's been reacting. But what we can't do if we do that is track how much carbon is moving around. It's very difficult to just to work out how much is being produced, how quickly, how it responds to temperature. You can't really do it looking at what's left behind. So we have two other options. One is that when these reactions happen, they can make things, they can make elements more soluble and come out of the rocks and then enter water and be washed away. And we can try and track those reactions in the water of a stream or a river. So we do that actually, and that's part of the Rock CO2 project. And I won't talk at all about that today, but it's another big strand of our research. But where this bit of this project started was, well, why can't we just look at the CO2? Why can't we just go and try and measure how much CO2 these rocks are producing when they react in the field and just measure it directly? That would be logical. But it was, at the start of the project, there'd been an attempt to do this. It had worked, but it's technically challenging because we thought that the CO2 produced might be quite a low rate. That was our inference. We also were worried that the CO2 coming from the rocks, how would we isolate that from the CO2 in the atmosphere, or CO2 in the soil from roots or from other phases? Like, how would we actually know that it was coming from the rocks? And that was something that was really important to work out how to deal with. Anyway, we went after this thinking, well, let's try and design a set of approaches to measure this, and that can be our starting point to take us forward. And this is where we went to do this. And this is what we call a critical zone observatory in our field. It's a place where we can go and study these types of reactions and how the water, the plants, and the rocks and the air are all interacting. And it's a beautiful landscape. You can see this. The rocks that you can see there are, we call these marls, and they've got lots of organic material. They've got lots of sulfides. They've got lots of carbonate. They've got all the ingredients that can produce CO2 when they weather. The two people in this image are important collaborators. This is Caroline Laboutier and Sebastian Klotz, who manage and run this observatory. So then there's measurements of all sorts of parameters being made, which are really helpful for us to scientifically contextualize what we've got going on. And this is part of the OSCAR network in France. There's a few of these sites around France where you can do this type of science. So a quick video, just a drone footage, just to show you. I think, how does this work? There we go. So we're now taking a flight over the catchment, and you can see, hopefully you see all this bare rock around, which is great for us. That's what we want to try and understand, how these these exposed rocks are reacting. There's a bit of forest cover you can see there as well. And in the shadows, these steep slopes. This is an environment that's really quickly eroding. There's lots of new rocks being always exposed by erosion. Now, as the image pans up, what you'll hopefully see is that this landscape's much more broadly, much more broad than just this single place. We're not looking at a quirk here. These rocks are often quite common. So you can see them in the distance of this area in the French Alps. So how do we do it? How can we measure CO2 coming out of these rocks? Well, this is where, there's an extensive group of people, many of whom have given presentations in these webinars previously, where we know that if we want to measure CO2 flux, one of the good ways to do it is using a chamber-based method, where you've got something producing CO2 and you trap the CO2 and you measure how quickly it accumulates. So yeah, this seems like a logical thing to do. So here's our CO2 being produced. So if you imagine that line I've put across the image being a surface, what we could imagine is, how could our chamber look? Well, our chamber could be on top of the surface. So here, imagine a box placed on top of the surface. So in soil respiration studies, for example, if you're looking at surface soil litter, you can have a chamber that will sit on top of your soil. So that was one option that we thought about, but logistically we were a bit concerned by it, because we were like, well, we want to keep measuring this over time. So how are we going to make sure we're measuring the same bit of the rocks, because they're going to keep getting washed away? So there was some logistical questions about why that might be quite hard to do. The other thing is that when you look at the signal you might expect from this chamber. So what do I mean by that? I mean, the surface area of the chamber, that's where the CO2 is coming from, and that's what we want to maximize. The volume of your chamber sets how much CO2 concentration you're going to recover. If your volume is really high, then you're going to have, say, 2 ppm per minute change, which might be too small because the instruments have drift. And so therefore, when you look at the key metric of a chamber, the volume to surface area metric is very important. So this is what this equation is showing you. What's the volume of that chamber and its area? And actually it scales with its height. So simply, if you want to increase the volume, you basically end up wanting to, if you want to maximize your signal, you basically want to make the height as small as possible, because that's going to increase the amount of area that you've got compared to the volume of your chamber. So we were scratching our heads about a few things. We thought, well, why can't we maybe install a chamber within the rock face that can collect these gases naturally and that we can return to over and over again? It's always the same bit of rocks that are kind of reacting. So that's a benefit. But also, if you do this with like a cylindrical chamber, you actually end up kind of winning a bit because the volume to surface area ends up being, this equation, fine, whatever. But if I just put some numbers in there and say, well, if my like cylinder is 2 centimeter radius, which is easy to make with a drill or something like this, and it's like 30 centimeters long, I would have a volume to surface area ratio that would be quite effective, and the equivalent of a chamber placed on the surface, that would only have to be 1 centimeter high, and that's really difficult to make a centimeter high chamber. So by making this thing in the rock, we get way more signal, and we're going to be able to measure a much higher concentration of CO2 because we've got much more surface area contributing to our volume. Probably should have just started with that and said, well, we decided to do it for these reasons. But this is where we started. It's like, well, how are we going to do it? What kind of CO2 concentrations are we going to be able to measure, and what's going to happen? So we settled on this idea of an internal chamber. And we did some tests on a field trip in October 2016, where we installed some of these chambers in this catchment, and we weren't quite sure what to expect. We sealed them up, like I show in this image. We're using like a bung, and we've got some glass tubes with some tubing, and then we clip the tubing so we can kind of seal our chamber. It's in the rock. The rock is naturally fractured naturally weathering, and it's leaking carbon into our little chamber within the rock face. So when we first did this, and we took, I think it was a EGM4 that we took along, and the screen on the EGM4, it was quite an old instrument and it was quite hard to read. So we installed this thing, we left it overnight, we went back the next day and we plugged it in, and to our great surprise, the PCO2 in the chamber was jumping up, was rapidly increasing, so much so that we couldn't read the digits properly. We had to download the data properly to look at it. And we ended up with over 3,000 ppm that had been collected within this chamber overnight. And that blew us away. We're like, okay, this is totally doable. We can measure these fluxes. There is enough CO2 being produced that the instruments can measure them. So this was in October. So in December, Guillaume went back and installed a set of chambers in this catchment. And we talk about this method in this paper from 2018, where, yeah, we install it, we seal it, and we're able to then keep coming back to these chambers over and over again. The next bit we needed to do is to be able to trap the CO2 to confirm that it's from the rock reactions and not just from a leak in somewhere, or maybe we've got roots coming through. Like, how are we going to work out that this is the rock reaction? And so we need to trap the CO2 so we can measure its isotope composition. Here's a couple of photos. We actually, at the French side, we were already quite a way into using these chambers when Tobias Royland started his PhD, and we went to New Zealand right at the start of his PhD to see if we could kind of install these chambers and learn something from quite a short trip. So one of the aims was over say 7 days while we're there, can we make measurements that tell us about the controls on these reactions? And here's Toby installing the chamber, and here we were using a hand auger, which is commonly used for soils, not for rocks. So this was quite a laborious task. I don't think Toby got a picture of me doing it, but as a PhD supervisor, I was helping. I was pulling my weight. It wasn't all left to Toby, I can guarantee. Now, how did we actually deal with getting the gases? Well, this is where Mark Garnet's work comes in. This is a paper by Mark Garnet and collaborators, where they established this way of manipulating the gas through an infrared gas analyzer. That's not novel, really. But what they were able to do is manipulate it through a zeolite trap that could trap the CO2 and mean that you can carry that CO2 back to the lab in a stable condition and measure it. So early in the project, very early in the project, we were in contact with Mark discussing, can we use your technique? Is it going to work in this setting? And we started testing it immediately. So the idea behind this is, imagine our chamber. That yellow dot is a CO2 molecule being produced through the weathering reactions. It enters the chamber. It goes round, in this case, past the erga, which has got its own pump. Sorry, this is the EGM5 we're using here, and measuring CO2 concentration. So in this case, we've just got a bypass where gas is moving around in a circle, and we're just letting this CO2 molecule all the way around. Now, what we can do is change the plumbing of that, and we can then divert that CO2 molecule onto our zeolite trap. So instead of going just back into the chamber, we can actually get the CO2 out onto this material, take it away with us, and bingo, that's wonderful. So this is kind of Mark's technology has been absolutely critical to driving this project. Just a couple of videos now for a couple of minutes before I show you some of the results. I realize I have been talking a while, but the results have kept to the kind of the main points, and we can skim over, and we maybe come back in questions if people have got questions about it. But I'll just show a couple of nice videos that hopefully they work okay on your screen. This is just looking at the French site, just to give you an idea about, you'll see kind of the nature of the rocks. In the moment, I'm going to turn around and kind of walk across the landscape. And if you look at the kind of nature of the rocks, we can see that they're weathering on the surface. They're breaking down kind of loose under my feet as I walk down this hill and across a little gully. And on the other side of the gully, are Tobys's measurement site. So actually this was while here we've got the apparatus and the EGM5 attached to our chamber, making the measurements in the field. Here's an example of us doing this in New Zealand after a bit of rain. It's not always as sunny and nice weather when you're using these bits of kit. And then finally, just a short video of Guillaume and I working, I believe this was in February 2017. You spend a lot of time kind of diverting the gas, making repeated measurements. And this is what we end up with, which is very analogous to what you would do if you're trying to measure soil respiration. So this isn't new in itself. You attach the erga to the chamber, you measure some CO2 concentration. But what we're interested in is the flux over time. So we use a scrubber to remove the CO2, which you see those big drops in CO2. We're removing the CO2 from the chamber, and then we're letting it naturally increase as those reactions happen. And that natural increase allows us to measure the flux. And then we remove the CO2, we go down, every time we go down to about atmospheric CO2 of 400 ppm, and then we let the CO2 increase. Now there's some beautiful automated chambers out there, right, that just lift up and then they go back down, and they lift up and go back down. We can't do this in this case. We're actually doing this manually with a soda lime scrub. So we actually scrub the CO2 onto soda lime and throw it away. Or in the orange lines, we deliberately divert the CO2 onto our zeolite trap so that we can measure its isotopes and work out where it's come from. So I've got a quick, well, this is like a short video of me doing this in the, oh, I'll stop it so it's not talking. So this is me doing it. I don't know if I'll play this all through, but it just give you an idea. So here I've got the equipment attached, and I'm pointing to where the gas is moving through our apparatus. It's going into this case where we can control where the CO2 moves around. It's going into the erga, which is currently saying 500 ppm. And about 2 minutes ago, it was at about atmosphere 400 ppm. So this is our flux. This is our increase of CO2 in the weathering reactor as it's happening. So what I'm going to do next is actually take this CO2, I think I'm pointing at it, showing that it's going just round in a loop. So if you remember the video, so it's now going, the CO2 molecules just going back into the chamber, it's coming back round in a big loop. What I'm going to do now is try and divert the CO2 and put it onto this thing here. So you can just see a little image of it. This is the zeolite trap. Hopefully you can see that in the video. So this is a material that will trap the CO2. So I will now divert the gas of the chamber through this thing, and you'll see the CO2 declining because I'm trapping it. So here we go, I'm opening up the chamber. We use these clips as a way to make this quite versatile and easy to manage, rather than valves everywhere. So now the gas is moving through that trap, and you'll see the CO2 start to, well, you get a bit of kind of noise as you change the plumbing, right? But you'll see the CO2 start to decline in a moment. I was trying to video this while talking. There we go. Now you can see the CO2 starting to decline as I suck the CO2, and that CO2 is now on my trap. And actually, I have to kind of keep doing that several times to get enough CO2 for analysis. So typically, we might do that 10 times or something like that, or 5 times, depending on how much CO2 you've got. And here I'm just showing, you know, a day's kind of a day or a week's work of looking at these fluxes, making notes as we go, recording the data. So I might whiz a little bit through here, but basically, this is what we did. Multiple chambers. Here's Guillaume. We measure them over 2.5 years, returning every season to make new sets of measurements. And this was the data set we were starting to build up. The black line is temperature. Black and gray line is temperature in the chamber. So that's going from the winter months close to 0 up to over 20 degrees here in the kind of shoulder of summer. And you can see these other circles, these are from 2 chambers, are increasing with temperature over that window. Now, if you were measuring a soil litter, this wouldn't be surprising. This isn't new. These are rocks, and these are reactions that we expected to be much more sluggish, and we weren't expecting to see this kind of response. So actually, when we got to this point of the project, we had no idea what was going to happen next. We thought maybe we perturbed this system, and actually the CO2 is just going to keep increasing for a bit and then come down. And it's just a fluke that as we started measuring when it's cold in December, and then it increased, and maybe it's going to carry on increasing. So that next trip after this trip was really, really a massive part of this project, because we didn't know how things were going to look, and actually didn't clear it up. It wasn't until the next winter when we got a bit of a clearer idea. So here's the full data set as it stood. And it was this trip in the middle, right in the middle of your graph there, in February 2017, when we saw the fluxes come back down, where we were like, hang on a minute, this is something we need to keep measuring as much as we possibly can. So hopefully what you'll agree with me here is that every time we were going to the site and building up this data set, we see this kind of seasonal pattern in CO2 flux. So in the warm summer seasons, it's higher, winter seasons, it's lower. There's other variability going on. We can see that one chamber is higher than another chamber. So I'll come on to that in a moment, but hopefully you just agree with my first order thing. And so the first order, when we just take the raw data of the flux that we've measured on each visit to the average temperature at each visit in the chamber, we get this correlation that can be described in the same way that you would describe a soil respiration process. Bit of jargon here, but basically what this is showing us is that for every 10 degrees that we warm up the rock, we get double the amount of CO2. So it's a so-called a positive feedback. So as things get warmer, we release more CO2. How am I doing for time? Yeah, okay, I'm doing all right. Other little like nuggets that we found, I won't dwell on too much, but are interesting, is that we found that the absolute amount of CO2 seemed to change as we got further away from the stream. So the stream in this setting at the bottom of the image and at the bottom of this graph, as we went away from the stream, our fluxes got larger, and we attributed this to two things. One, kind of the relative amount of air and water, because they can hold different concentrations of oxygen. Oxygen is one of our key reactants. So near the stream bed, we'd expect more water in the spaces in between the rock, and that would potentially lower our reactions. But actually, if we normalize all of the chambers, so that means we kind of look at them in the same relative to each other. So this is 4 chambers where we've normalized, in this instance, to the mean. You can see that they all collapse onto one another. So they all have slightly different absolute fluxes, but their relative fluxes are all swinging with the seasons in the same amount. Another important secondary control was right at the end of the project. We realized, hang on a minute, we've got some variability. What's it caused by? Could it be caused by rainfall events? So when it rains heavily in the catchment, what's happening? And at that point, we'd only been measuring, say, one chamber. We might measure it over a week, so maybe on Monday and Friday, and then the trip would end. And then we'd come back a few months later and we measure it again. So instead, Guillaume stayed in France and he measured over here from April 10th to May 10th regularly, and especially tried to get there after big flood events, storm events. So this graph is showing flux is changing, and the take-home message is that when a rainfall event happens, we see the CO2 flux changes quite rapidly, declines, and then it kind of bounces back. And so within about a day. So it's a kind of secondary control, but it's an important one and it's interesting. And we talk about this in the paper, about this maybe being washing the carbon into the river water. So maybe it gets released later anyway. And then overall, just to summarize these findings, the one on the right is the key one. This is multiple chambers. There's 5 chambers here with slightly different, natural variability. And they're showing this increase of CO2 release with temperature. And it's about the same sensitivity to temperature as some soil environments. Again, quite surprising given that we're talking about these rock reactions. So to finish, and I didn't want to dwell too much on this because I wasn't sure whether what the audience might be interested in, but I just want to highlight that we're using isotopes to unpack these two different sources that I mentioned earlier. And so the way that we do this with isotopes that we've heard about in these webinars before, carbon isotopes, stable carbon isotopes here, delta 13C. And then this vertical axis is our radiocarbon. Radiocarbon is so powerful for us because the rock minerals contain no radiocarbon. There's 0 on the scale. So the gray and the it's kind of a red star, they're our rock sources of CO2. And our atmosphere is up at the top at 1. So we can really nicely distinguish these sources using this array. And so here are our trapped gases. Again, don't worry, I'm going to skip quite quickly here and tell you that we then unmix where we think these gases are coming from so that we can link them back to the rock components that we're interested in. And so we do something which is called a mixing model or source partitioning, and we unpack things like this. I'm going to whirl through some of Tobys' examples because we did this in New Zealand, as I showed earlier. We installed these traps in New Zealand, and he measured over 7 days instead of over 2.5 years. So this is going from end of April 2018 to a few days into May 2018, measuring CO2 flux. We've got temperature on here, rainfall, just giving you some context. I won't mention that, but what I will show is that just like in France, we see this increase in CO2 flux as the temperature rises. So independently confirming from a different site, different type of rock, what's going on in France. So from the kind of earth sciences point of view, like in the bigger picture of this geological carbon cycle, this is a really interesting new development. And again, this might be a bit niche for the audience, but basically it's saying that we've got an important control on this reaction by temperature. So on this graph, we can see an important one control I didn't talk about, which is this thing where we supply more material to react, we can increase the flux. Here I'm saying that actually we also have a temperature control. So if we're cooler, we might see less of the CO2 being released. Warmer, we're going to see more. And that releases more CO2, which makes it warmer, which could release more CO2. So we have this so-called positive feedback that hasn't been recognized before. So the questions now that spin out from this is, and people ask us about this all the time, have you just measured a quirky place where these are the only places where this is happening? Are the fluxes large enough around the whole world for this to be important? That's another key question that we need to address. And 3, if you're right, what happens to those other pathways? So I talked about that right at the start, a pathway whereby CO2 can get drawn down. So how does that reaction need to change? And these are all things that we're trying to tackle moving forward. So I'll put a few bullet points summarizing the scientific results. There's also a review paper that we wrote on some of these themes if you're interested more generally in the geological carbon cycle. And yeah, just to say, there's my email. I'm on Twitter occasionally and happy to take any questions now or later. Thanks for coming.
Thank you very much, Bob. I really appreciate it. We all did. And I've also put a link to his paper in the chat if you'd like to check that out. And I can also include it in the email when I send out a link to the video after. But if you have any questions, let's see. We have you established a correlation between CO2 emissions and soil rock moisture content?
Yeah, the answer is no. We've looked at it because we have humidity probes in the chambers at the same time as temperature. So not in the same chamber we're measuring the reactions, we have another chamber of similar dimensions and we have a humidity probe in there. And what we found in this site in France is that it's 100% basically humidity all the time in the shallow rock phase. That doesn't mean the rock moisture doesn't change through the year, because I've just mentioned after a rainfall event, storm, there's more water around. We definitely see that impacts the CO2 flux. But there's a kind of ambient moisture there, a lot of ambient humidity. What's interesting, so in answer to your question, we see we can't ascertain whether if you take all the moisture away, will the reactions slow down and stop? That would be very interesting. And in our site, we can't tell. I can't tell you that. But clearly, yeah, the temperature here is driving the response. Yeah, hopefully that answers your question.
Okay, Alicia says, thank you for the answer. So it was satisfactory. Does anyone else have any other questions? He's a hard guy to get hold of. You put your questions in now.
It took about 2 years to do it.
I know. Oh, we have you measured air pressure? We've noticed strong negative correlation between flux of CO2 and air pressure.
Yeah, so we're using the EGM5. EGM5. So it's measuring pressure, and so when we use the PCO2 measurement to assess flux, you know, one of the bits of that pathway, right? Because you want to look at mass of gas, so you need to correct for pressure and temperature as well. Although the temperature correction is quite minor, and actually, to be honest, the pressure correction is quite minor because we're pretty much at ambient atmospheric pressure in this situation. But it's an interesting one. So I guess your question might be sort of methodological, like how do we worry about that? But yeah, certainly if you convert to mass of carbon, then you have to take the pressure into account, and I think that's where I would go with that.
Can you distinguish between rock CO2 and biological respiration by endolithic microorganisms?
Oh gosh, this audience, yeah, I've gone too superficial, guys. So I'm really sorry. Yeah, no, that's a brilliant question. So I think what you're asking are, yeah, do these microorganisms that are kind of subsiding on phases within the rocks, can we see any evidence for them, essentially? So we have some new evidence that shows that there's a reasonably extensive microbial community in this weathering zone using phospholipid fatty acids, and we're looking at the DNA extracted from these rocks as well, and we find an aerobic community, broadly speaking. Now, what role are those microbial communities playing in this reaction? That's an absolute key question that we can't get at yet because we're just measuring the products. But my gut feeling is that we would find a community of microbial organisms that is using the rock organic carbon as their substrate. So you would expect that microbial community would be radiocarbon depleted, and you know that community itself will be releasing CO2 with no radiocarbon because they're using the rock substrate. But this is really, you know, unpicking whether this is abiotic or biotic is really critical to know how the reaction should propagate. So you hit on a really important theme with that question. Mm-hmm. Thanks.
Okay, great. Okay, very interesting. Such a cool idea. So Fiona Darcy, she studies volcanic carbon by using stable and radiocarbon in tree rings to track past CO2 release in volcanic areas. She said she noticed some excellent trees in the drone videos, perhaps another good co-correlation. She also finds it hard to delineate precipitation, temperature, and biogenic factors.
Yeah, so Fiona, brilliant question. And one of the things that we were doing, so this is slightly related, I think, so trees, this would be a wonderful archive, wouldn't it? But you're absolutely right that the tree is going to take what's there. And so, you know, if you've got this leak of radiocarbon-free CO2, in your case, volcanic degassing, in our case, this weathering source, you know, how is it going to make it into the tree day to day, and can we spot it? I definitely know of work in ETH Zurich where they've looked at some springs in the Alps where trees around hot springs are radiocarbon dead. You know, but that's like they've been swamped with CO2 with no radiocarbon in it. But actually, one of the things we did try and do was measure the atmosphere, and we were actually doing that to work out what one of our M members were. But we have tantalizing data. It's tantalizing. and it shows that the radiocarbon content of the atmosphere of this valley looks like it's got less radiocarbon than you would expect. And so that's consistent, right, with this reaction happening everywhere. And actually, one of the things we were chatting to people about is whether we, can we scale this up so that can we use the atmosphere actually to try and scale this up? So instead of just looking at the local reaction, can we try to use radiocarbon in the atmosphere to say how much flux is happening over this whole area, this much, much larger area. So we haven't started that yet because the signals are very small. It's probably like your volcanic, the volcanic degassing community have the same kind of thing. It's like, if you're in the plume, you've got loads of it, but actually what lots of people are now interested in is this diffuse degassing, which is much harder to measure. So thank you for stimulating that. I probably went off on a tangent, but yeah, thanks.
Okay, great. And her response is exactly, that's where the radiocarbon comes in.
Yeah.
But the atmospheric and soil CO2 sources combine and make it difficult. And she
I
says,
could see that.
Yeah.
Well, good luck with the research. It does sound really fascinating.
Do we have anyone else who'd like to ask a question? A lot of thank yous, a lot of appreciation. Okay, well,
Great. Well, thanks everyone for coming. I really appreciate it. Yeah.
Oh, and thank you. And we appreciate you sharing the trials and tribulations and then what you actually designed, to make it work.
As I said to you, and I didn't know quite, I thought this is like quite a nice place to do that, because if you're presenting in a conference, you just don't have enough time to talk about that.
But that's really valuable, for people to understand what you've done and generous to share, because that was quite a lot of work for you to sort it out. And I'm sure it was well appreciated. Maybe we'll find a way to just present that in an application note or something for someone, because I think there's a lot of students that would really benefit from it as well.
Cool. Yeah, we've got a little application note we wrote with you a few years ago, I think, on this, haven't we? But yeah, it might be that it's interesting to think about whether we could add a little update to it at some point. Yeah. Sure. Sounds good.
Well, thank you very much, Bob. We really appreciate you taking the time to present this. And for everyone who has questions they think of later, feel free to email it to me and I'll respond to Bob, and we'll make sure it gets answered. And this will be up on the website sometime next week. And Bob, I'll obviously send you a link as well. But thank you so much for your time. We really appreciate it.
Absolutely no problem. Yeah, thank you. And thanks for the great set of questions. That's brilliant. Thanks.
Yeah, there are a lot of good questions. All right, thank you.
Well, take care. See you again soon. Bye.
You too. Bye-bye. Thank you for attending this webinar. To learn more about Dr. Hilton's work and about our soil solutions, visit pbsystems.com.